Hello everyone. So after splitting those surfaces, we gotta keep going down the tree. And so this next part may get a little confusing. This is just the workflow that I found the fastest. So what we ultimately need to do is we need to make regions, right? But in order to do that, we have to have a mesh. And once you make regions, you have to remesh it so that the mesh incorporates the regions. So typically what I do is I make a very quick coarse mesh, then I define all my regions, and then I go and make my detailed mesh. But we're getting a little ahead of ourselves there. Let's go over how to make a mesh in the first place. So what you gotta do is once all the surfaces are split, you go to operations and you hit new. Now there are gonna be three options here. Because we're doing the cavity method, everything was handled in CAD and everything was imported in perfectly fine surfaces. So we don't need to do any of the surface preparation to Boolean. What surface preparation is as you can see through all these options, it's preparing the surface for meshing. So let's say you import a part in that isn't the best geometry. Maybe someone did it, and maybe it's not your part. Someone did it really quickly, and there are, say, intersecting surfaces, or there are surfaces that are not closed, or things like that. Or, for example, maybe you're making a change to the CAD. Maybe this is another iteration. Say you want to fill a hole, you want to extract some volume, you want to change some parameter of it. You can prepare the surfaces for meshing through here. Boolean refers to Boolean operations, and this is kind of more of a universal thing in a way, but Boolean operations are, you have these different bodies, and you can either combine them into one, you can make them intersect, so that way it's just the intersection exists, or you take away the intersection, subtract, you get rid of a body based on another body, imprint. I haven't really done these two, but that's just a Boolean, but we don't need to deal with that since we have the cavity. Mesh is what we're dealing with. And so we can just go to automated mesh because I just let the program handle everything. Now, I don't know if this is the best way for meshing. I would be very surprised if this is the best way. But anyways, this is what I've been doing. It's been working for me. It's not optimized, but if you're in a hurry, this has been working. So, automated mesh. Now, it'll bring up this menu here, and if you have multiple parts, they'll all be shown here. We only got one part. So what you do is you select the part, and that's telling Star-CCM, hey, I want you to mesh me this part or these parts here. So now you have to select the meshers down here. So you got surface remesher. As the name implies, it remeshes the surface because, again, we imported surfaces, remember, from the Parasolid file. Optional surface remeshers include automatic surface repair. I always just click that in case. And again, if the surface is malformed, if there's bad things in it, this should handle most of the smaller stuff, but anything worse or bad you have to manually do yourself. Now you have volume measures, and so the main difference between a difference between surface and volume meshes is the surface only meshes the surfaces, as the name implies. A volume mesh makes a volume. So this surface here, think of it as hollow in a way. All of these walls, everything has zero thickness to it. And when you do a surface mesh, it will mesh those surfaces, but that's it. What a volume mesher would do is it will fill in all of that empty space there and make actual finite volumes that has an actual volume. But anyways, it makes finite volumes and fills in that space. So now instead of, think of this instead of being now just a paper mache where you just have a piece of paper for everything. Now it's a solid box. It's like a cube. It's solid. So you gotta select your volume mesher, because what Star-CCM does is first it does a surface mesh, goes through and makes a surface mesh, and then it goes through and makes the volume mesh based on the surface mesh. So you got three options: polyhedral, tetrahedral, and trim cell. To be honest, I don't know what trim cell is. I maybe knew at one point, but it wasn't that important, so I don't remember it. Polyhedral and tetrahedral are two different things. So, as the name implies, tetrahedral mesher uses triangles, essentially, or tetrahedrons in 3D. And polyhedral mesher uses polyhedrons to mesh. So, I always go with polyhedral mesher because tetrahedron is limited to 3 sides as a triangle in 2D, or how many sides in 3D? 1, 2, 3, 4, 8 faces, I believe, in 3D. Now, this can work for simpler parts, but then you're limited on elements and nodes. I'll make a more detailed video on what meshing really is, but this is kind of just more of a quicker video on how to set up the mesh. But you're limited on elements and nodes for tetrahedral. Polyhedral, I think in Star-CCM, if I remember correctly, it can be up to 32 sides, which means you got a lot more elements and nodes and fill in space a lot nicer. So I always go with that. Now, optional volume meshers and optional boundary layer meshers. So, thin mesher, this is if you have very thin surfaces like thin walls. We don't really deal with that, so we don't need to worry about that. Boundary layer meshers, prism layer mesher, and advanced layer mesher. This is for advancing layer mesher is a way of controlling the mesh more finely from a surface out into, say, infinity in volume. You can kind of control the layering better, but I don't really deal with that. Prism layer mesher is the one I do use, though, for the boundary layer meshers. So, again, I'll make a more detailed video about this when I have the time, because I want to actually plan this out. But the prism layer, so every surface in air or water fluid has a boundary layer. If you're not familiar with that, I suggest you brush up on basic aerodynamics. But very quick overview with no pictures. Boundary layer is the layer of air that, or fluid that is forming on the surface where viscous effects cannot be ignored. Now, prism layer meshers, what this does is it creates prism layers on the surface that keeps inflating out into the free stream air, which is where viscous effects can be ignored because it's mainly inertial effects that take effect there. And what it does is it makes thin layers across surfaces. And you'll see this when the mesh actually gets made. But anyways, select that, and we're good. So, when you see this option here, you'll see that what that means is it needs to be done. So, if there's a little cautious sign there, that means something has changed or something needs to be done, and the action's not completed yet. So, as you can see, we got our meshes down here. We got our default controls. Now, default controls are, what controls this automated mesh. So, let's go through them real quick. So, base size. This is, well, and remember, if you ever lost, there is kind of a little thing down here that tells you what it is, as well as the Steve portal, which you can get help on, or online. So, base size. It's the reference length for, as it says, reference length value for all relative size controls. This is essentially what the base size of your mesh will be. Or, sorry, the base size of your cell in your mesh will be. So in this case, we're saying it's going to be a base size of 1 meter. Now, CAD projection, I don't actually know what that is, but I don't touch it. Target surface size. So, again, remember, these are surfaces. Now, what this is telling is this is saying to Star-CCM, I want you to try to make all the surfaces this size. Or I want to make all the cells on the surface this size. So, again, remember, a mesh, let's say, like, it's 10 little shapes, 2D shapes, right? So in this case, if we leave it default, what we're doing is saying that I want the cells to be around 1 meter, like each edge to be around 1 meter. That's really big for what we're doing. So you want to bring that down. I generally bring it to 0.1. So I'm like, all right, I want these cells to be at least 10 centimeters. That's pretty big still, but not unreasonable for the things that we don't really want to have a lot of detail on. Now, minimum surface size. This is telling the program, alright, so I can mesh this to be infinitely, well, not infinitely, but very, very, very small, right? But what's the limit? How small do I want it to be? Where do I want to cut that off? And so, again, this is kind of big for what we're doing. So, what I usually do is I bring this down to about 1 centimeter, and that usually makes it okay mesh, or that usually is generally good. Surface curvature. So this is telling. Oops, didn't want to bring that up. This is telling the program. All right, so see how we have curves here. Now, obviously, when you're trying to make a mesh out of this, it's going to make all these flat faces, right? This is telling it, all right, so around curves, well, first we have to enable this. We have to say, all right, so curves, we want it to be a little more enhanced. We want there to be a little more surfaces around here to really detect that. So, in this case, we're saying, so, again, we have a circle, right? Think of a curve as like being a complete circle. This is saying, how many points will it draw on that? And then this is saying where the maximum number of points it'll draw on that. And so from there, it uses those points to help make more faces to help resolve curves better. Generally, this is just through trial and error. I just do 60 points per circle and then a maximum of 360 points per circle, so it's basically like 1 point per degree. Curvature deviation distance. Again, I've never played around with this too much, but this is only more important, again, when you get to smaller sizes. This is basically saying you don't want the mesh edges to exceed this distance from the geometry. So again, remember, you're trying to make a curve out of flat surfaces. Those surfaces are going to jut out slightly, right, from the base geometry. This helps control, alright, I don't want it to stick out too far, so if it goes beyond this, I'm going to stop it. I'm going to cut that off. So again, around larger curves, you know, about a centimeter is fine, but like around finer curves, like smaller wings and all that, maybe you want to drop that down to like a millimeter or something like that. But as the base, as a default control for the entire domain, you don't need to worry too much about that. Proximity, again, so this increases the number of faces based on distance to nearby surfaces. So basically, if you have a ton of surfaces by each other, this will increase faces, so that way it gets resolved better, those gaps and all that. So again, proximity, I basically just turn it on, but I don't really do anything to the actual numbers because they typically work fine. Growth rate. So what a growth rate is remember, what we're doing is we're meshing the surface first, right? And then from there we're building, when the volume mesher comes by, it builds volumes, and it makes these finite things. So what's going to happen is the growth rate, let me go back to that. The growth rate is controlling how the volumes get bigger as they get further away. So, you know, for example, it's going to be smaller around here because you have all these things, but once you get out far away from a surface, like say out here in this region, you don't need them to be super small, right? But remember, we set a target size and a minimum surface size. So out here, it can go ahead and just say, I'm just going to hit the target surface size. I don't really need to go, and I don't need to get anywhere near the minimum surface size. But how do you control how it goes from this small size to a big size? This growth rate is what you use for that. So what it does is it creates a ratio between every connected volume. So one cell will be, let's say, 1 centimeter, 1 square centimeter, right? Or 1 cubic centimeter. Then you go out, well, I don't really want to think about cubes right now, so let's just say 1. And you go out 1 cell. That cell will be 1.2 times the size, or in this case, 1.3 times the size of that cell. You move out 1 more. That's 1.3 times the size. You keep doing that over and over. By default, it's 1.3. I generally like doing 1.2. That's kind of the default in ANSYS, and that's also something recommended in a meshing paper I read. I'll put a link in the description to the meshing paper because that's kind of where I get some of these numbers and domain boundaries from. But anyways, auto repair minimum proximity. Just don't worry about this. This is basically just saying when will the auto surface repair kick in. Basically, if you have like surfaces too close or gaps too big. Number of prism layers. This controls how many prism layers grow from the volume. So default's 2. It's saying, alright, we'll get 2 extra layers here, and then we go to normal mesh. I generally do, as default, 5. I keep saying default because you have custom controls, which we'll get to in a sec. But I usually do 5, so we get 5 layers going up. Prism layer stretching. This specifies the thickness of each layer as a ratio. So again, it's basically the same as the surface growth rate. Just this is just for the prism layer, so I just bring that down to 1.2. Total thickness. Now, there are proper ways of calculating this. I vaguely know how to do them through my turbulence class. I've never actually applied it. I need to go through the notes again. But there are proper ways of scaling this, and if I remember correctly, the only real way you can do this is you have to run it first and then calculate it. What I usually did was I just made it a absolute thickness. I never really calculated the thickness of the boundary layer. So that's something I know I can improve on in my meshes and my simulations, but for now, let's just go ahead and make this an arbitrary number. This, again, has been through trial and error, what seemed to look good. I usually do just about 10 centimeters or so. And mesh density is just 1. Like, you make the meshes denser or, you know, less dense, things like that. And so that goes to all the default controls. Now, custom controls, remember how I was saying how we label everything? this is important because if you want to make a custom control and do so, curve surface part volumetric control. We do surface control because we have surfaces. What you can do here is you can specify a specific surface, and then you can go through all of those controls again, but make them specific for that surface. It's because again, you want the wings to be more resolved. You don't really care about the body so much, things like that, right? So that's why you go through and do that. Now, I will not do this for now. I will just go through the domain mesh just to show you. Hopefully this doesn't take too long. It's just a wing, so it should be fine. So we got all the default controls down. Automated mesh. Now, per part meshing, what that does is if you have multiple parts, it'll mesh each part separately. We don't have multiple parts, so we don't need to worry about that. This helps optimize the meshing process for large assemblies. I haven't really played around with it. I don't know how well it works, though, so can't tell you that. Mesh execution mode tells you measures if you want to do it in serial, parallel, concurrent. Generally, I do serial because I know parallel is, faster, but I've heard that there's sometimes problems when it comes to boundaries, because what happens is when you do parallel meshing, it splits up the domain into different parts, and then it gives each processor that you're allowing Star-CCM to use part of it to mesh, and then it joins them all together. But sometimes those mesh boundaries, like the different parts that each processor made itself, when they join together, sometimes there can be errors, so I've kind of shied away from it, but I should play around with it more. Input parts, now by default, it's going to be all the parts that we selected, because remember when we selected the parts for the automated mesh, that's automatically populated, so we don't need to worry about that. Then everything else you don't need to worry about. So, when you go in mesh, first you gotta make the surface mesh, which is this little icon right here, generate surface mesh. That's right. So, that little error message, it's angry because we haven't made a continuum for it yet. So what's happening is because I have volume mesh selected already, it's trying to make a volume mesh as well, but we don't even have the surface mesh made, so we gotta go and unselect that, and let's just make the surface mesh. So again, how Star-CCM works is it makes a surface mesh, and then from that surface mesh it makes a volume mesh, and I forgot to make it generate a mesh scene. So we'll go down here, say new scene, mesh, and this is our surface mesh. As you can see, it's not the best, and that's why we need those custom controls for refinement, but as a global domain this is fine. So now that we have the surface mesh, we can go ahead and add a volume mesh. And as you can see, it saves pretty much everything, so we can go ahead and once you have the surface mesh, we can generate. Okay, my bad, I forgot. We have to make a region, and from there we make the mesh. So anyways, I forgot, before you can do the volume mesh, you have to go and create a region under regions. So what I did was I went through, made a region, then you have to go through and select the parts. Now, when making the region, make sure it's a fluid region, because again, this is a cavity. And parts, make sure you go and select our domain here. Now, physics continuum, we haven't made one yet, so don't worry about this. Mesh continuum, it will automatically generate one, so don't worry about that. So, let's go back to our automated mesh, and I think it should just fill in. There we go. Yeah, so it'll automatically connect that region you make to the volume mesh, so sorry about that, but yeah, so now it's going to generate this volume mesh, and hopefully this won't take too long because it's not too fine. Also, it's only just the front wing, but yeah. So yeah, as you can see, the volume mesh is finished. And remember, down here you can see all of the information for your mesh. So this was the surface mesh, this is the volume mesh. You can see this is how many cells we have, this is how many faces we have, this is how many vertices we have. So if you can imagine, we already have like 170,000 faces and almost 40,000 cells for just the front wing alone. You can imagine how big a full car gets. It's several million. So meshing can take a little while. It can take a little while, especially when we refine everything. But anyways, let's go down to our scenes and let's look at our volume mesh. So as you can see, this is the polyhedral. You can see, many sides. Polyhedral is the name. And here is the volume mesh. And you can see this is pretty bad. It's not refined enough. That edge is nowhere close to being round. Same here. So that's why we need local refinement. I'm just checking because it doesn't look like the prism layer is meshed. Anyways, yeah, so I'll get into custom controls in a bit. I'm just checking the regions real quick. So as you can see, the mesh continuum in the regions automatically gets populated to this parts mesh. And because we did this mesh, it automatically generated a physics continuum. So, well, because, yeah, we made the region, we meshed it, we have a physics continuum. So, I'll cut the video off here. Now, as I said in the beginning of the video, my next steps from here is I define all of my boundaries in my region, and then I remesh it, because when you make a boundary, you have to remesh so the mesh knows what boundary is what. So, I'll cut it off here, and the next video we'll go into boundaries, and we'll go into the custom controls and refining everything. So, yeah.